Okay, let's continue. This is the second part of our discussion of section 1.2, which is about Boolean algebra and logic gates. Let's take a look at some more examples and simplifying examples of algebraic manipulation of Boolean functions. We have here the first example. We have x, then open parenthesis x prime or y, close parenthesis. Simplifying this, we apply the distributive property. So it becomes x prime plus xy. Then x prime, we know that this is equal to 0. So 0 plus xy equals xy. So we have simplified x times x prime plus y into xy. For number 2, we have x plus x prime y. How are we going to simplify this? We applied the distributive property of OR to over and. So x or x prime, and then multiply or AND it with x or y. We distribute the OR operation. And we know that x or x prime is equal to 1. So it becomes 1, then ANDed with x or y. So the simplified version of this is x or y. For the third example, we have x or y ANDed with x or y prime. So we distribute each. So it becomes x xx, which is just x, then or we OR it with xy prime, then the second element yx. For in this case, from the book's case, it distributed this whole quantity into the first element here, x. That's why xy comes first, then xy prime. Then last element is y prime. So how are we going to simplify this? Combine all x with the same elements, so it becomes x factored out x, which is the common element, times 1 plus y prime. Where is y prime? This is just equal to 0. So the result is x, you AND it with 1 or with any of this whole quantity is just equal to 1. So the final answer, the most simplified answer, is x. So x or y ANDed with x or y prime is just equal to x. Also, xy, number 4, xy plus x prime z plus yz. How are you going to simplify this? Combine. It did not combine. Which is a different way. The author, he has a different way. The author manipulated the last term, yz. So he multiplied it by 1. This is x plus x prime is just 1. Why he chose x plus x prime is because this 2 has the elements x in it, but yz doesn't have x. So it multiplied 1, which is just an identity element. So it becomes xy plus x prime z. Then distributes xyz or x prime yz. And then it factored out xy, which becomes common to the first and the third elements. So xy times 1 plus z. Then factored out the second and the fourth elements. The common is x prime z, becomes 1 plus y. Anything that is ordered with 1 is 1, so this is 1, this is 1. What remains is xy or x prime z. So what happened? yz is eliminated. So xy plus x prime z plus yz is just equal to xy plus x prime z without the yz. Number 5. Quantity x or y ended with the quantity x prime or z ended with the quantity y or z. What happened here? It says by the duality from the function 4. Okay. Using the data in function 4, we are using the duality property of the Boolean operators or and AND. He made this function number 4 is the dual of the function here. Instead of xy, it becomes x or y. Instead of or, it becomes and. The same elements, so we just interchange the operators from or to and then from and to or without complementing. They're not complementing, or just using the duality property by interchanging the operators. So we expect the result to be also in dual form. So the dual form of this xy or x prime z is, instead of and, we use or. So x or y, then instead of or, we use and. Then instead of and, we use or. So the answer for number 5 using duality property is the quantity x or y ended with the quantity x prime or z. The fourth function illustrates the fact that an increase in the number of literals sometimes leads to a simpler final expression. The author is referring to this case here, where he multiplied an identity element, an identity which is x plus x prime, this is equal to 1. It leads to a simpler function expression. Function 5 is not minimized directly, but can be derived from the dual of the steps used to derive function 4. Function 4 and 5 are together known as the Consensus Theorem. It is called the Consensus Theorem, where we predicted the output using the duality property, since these two functions are dual of each other. Complement of a function. F prime, this is the complement of a function f. The complement of a function f prime is obtained from an interchange of zeros for ones and ones for zeros in the value of f. Example of evaluating the complement. So a or b or c. Let's find the complement of this function. This is equal to a or x, then prime. Let b plus c equals x. So many theorems, and then we finally arrive to the final answer that the complement of a or b or c is equal to a prime, b prime, c prime. just using the Demorgan's theorem. You can apply directly the Demorgan's theorem to find the complement of a function. Let's go to another example. Find the complement of the function f sub 1 is equal to x prime y z prime plus x prime y prime z, and f2 is equal to x ended with the quantity y prime z prime or yz. Solution of the complement of this function: we apply the Demorgan's theorems as many times as necessary. The complements are obtained as follows. So you have here f1. What we are looking for is f1 prime and f2 prime. f1 prime, we add prime here to the quantity. Applying the Demorgan's, we first perform the Demorgan theorem from this OR operation. So instead of OR, we put AND here, and then we complement each term. So x prime y z prime, we complement that, and then x prime y prime z, we complement that. So this is the expression, resulting expression, and then we simplify using the Demorgan again. So we OR these terms here, x or y prime, and then complement each term. So instead of x prime, using the Demorgan's, it becomes x, and then y becomes y prime, and z prime becomes z. Same with the last term. Complement of x prime is x, and then instead of multiplication, we use, instead of AND, we use OR. As for f1. So this is the complement of f1. This is f1 prime. We can still further simplify this using distributive property, but sometimes we can just leave it like that in factored form or in multiplied form. For f2 prime, with the complement of f2, and again we apply the Demorgan's theorem. Let me write it down so that it will be much easier. Let's solve it. f2 prime. Oh wait, f2 prime. Our f is x times the quantity y prime z prime plus yz. Right? That's our f2, and then we complement that because that's what we're looking for. The complement of f2, applying the Demorgan's, we start with this and this whole quantity. So instead of AND, we use OR. Instead of x, it becomes the complement. Then copy the expression and we take the complement of that. So copy x prime, then the complement of this by using the Demorgan's theorem. We start with the operation. Instead of OR, we use AND. And then we complement this expression y prime z prime, complement, and then yz, complement. Simplifying further, again we take the Demorgan of that. So instead of multiplication, we use add. Instead of y prime becomes y, and instead of z prime it becomes z. Copy. And here instead of and, we use OR. It becomes y prime plus z prime. let's distribute. So y prime plus zy prime. Is it right? No. Wait. It's y or z y prime. And then y or z with z prime. Distribute y prime plus zy prime plus yz prime plus cz prime. This is 0, this is 0. What remains is x prime plus y prime z plus yz prime. Let's check the book's answer if it's the same. So x prime plus yz prime, x prime plus y prime z plus y prime z, so the same. So that's how you simplify or evaluate the complement of a function. You apply the Demorgan's theorem many times until the expression is simplified. Next, let's go to the canonical and standard forms. Okay, let's continue. Let's define some terms. I'm gonna try to establish the canonical and standard forms of the Boolean expressions. Mean term, this is the standard product. For example, x prime y prime or x prime y. We are multiplying or we are ending the two terms. Max term, we call that the mean term. For max term, this is a standard sum. For example, x prime plus y prime. So we are using the OR operation for each single variable. A Boolean function can be expressed algebraically from a given truth table by forming a mean term for each combination of the variables that produces a 1 in the function, and then taking the OR of all those terms. That's a. It says that we can express a Boolean function is a sum, combination of mean terms. Let's try to check the table. Table 2.3, this is the mean terms and max terms for 3 binary variables. So if we have 3 inputs, 3 binary variables, x, y, z, the mean terms are, there are 8. We know that the inputs can have, or the variables, when there are 3 inputs, this can have a total of 2 to the 3 or 8 possible combinations. And the equivalent term, mean term for that is, there are also 8. The mean terms for x, y, and z. It will be easy. If it's 0 here, then we write complement of that variable. So 0, 0, 0. So it's x prime, y prime, and z prime. Another example, 0, 1, 1. Since it's 0 here, so our x will be x prime. So x prime, then since it's 1 and 1 for y, z, we take them as is, which is y and z. 0, 1, 1, the equivalent mean term for that is x prime, y, z. and it is denoted by the small letter m, and then the subscript is 3. This is in the right order. M0 for the mean term x prime, y prime, z prime, and this is 1 as defined here. A mean term for each combination of variables that produces an 1 in the function, taking the order of all those terms. This is 1. This expression is 1 if x, y, z are all 0, right? And for example, this is 1. This mean term is 1 if x is 0 and y and z are 1, right? Because if we end 0 prime, that is 0 prime is 1, and then y, z are both 1, 1, so 1, 1, 1. If you end that, the result is 1. We have mean terms from 0 to m0 to m7. For max terms, we have the OR for each function. For the max terms, if it's 0, 0, 0, then we don't complement. It's just x ORed with y, ORed with z, because we have 0, 0, 0, so it's the opposite of the mean term. For the mean term, if it's all 0, we use the complement of each variable and then we end them. Excuse. For the max term, if it's 0, 0, 0, we don't complement. We take them as is and then use the OR operation. For example, 1, 0, 0. So it's 1, so we complement for the max term. So it's x prime, then 0, 0 as is for y and z, and then use the OR operation. And that is denoted, the max term is denoted by the capital letter M. And this is already in the right order with the inputs x, y, z from 0 to 1, 1, 1 or 8, decimal 8, I7, 0 to 7. So mean terms max terms, capital M, 0 to 7. Try to remember these mean terms and max terms because we will be using them a lot. Boolean functions expressed as the sum of mean terms or product of max terms are said to be in canonical form. If we use the sum of mean terms, so the sum of these mean terms or the product of these max terms, that is classified as in the canonical form. Let's look at some examples. Sum of mean terms. The mean terms of sum defines the Boolean functions are those which give the ones of the functions in a truth table. We've already discussed it previously. So example 2.4, express the Boolean function f equals a or b prime c as a sum of mean terms. How are we going to transform this as the sum of mean terms? This is not in mean terms form, right? Although we have the sum here, but a is not a mean term and b prime c is not a mean term. How do we know that they are not mean terms? Because we know that the inputs are a, b, and c. We have 3 inputs, therefore we are expecting that the variables in the mean term should contain 3, both a, b, and c. The function has 3 variables, a, b, and c. The first term a, missing 2 variables. Yeah, the first term here, which is A, doesn't contain B, C, B and C. Therefore, A is equal to. So how are we going to find the mean terms associated with A? This term. So it multiplied the identity element 1. B plus B prime is 1. We know that B plus B prime is equal to 1. So we are just multiplying 1 to A. So therefore A is not changed in this expression. So it's valid to multiply A by B plus B prime because this is just equal to 1. So applying distributive property, it becomes AB plus AB prime. This function is still missing one variable. It still lacks the variable C. So we multiply again by 1, which is C plus C prime for each term, AB and AB prime. So it becomes AB times C plus C prime plus AB prime times C plus C prime, which is 1. This is 1. And then applying distributive property, it becomes ABC plus ABC prime plus AB prime C plus A prime AB prime C prime. The second term, so what happened? We already have the mean terms. We have 4 mean terms for A. So A is equal to this. This is just equal to A, this whole expression. We just wanted the mean terms equivalent of A. Second term is B prime C, is missing only the variable A. So we multiply by 1, which is A plus A prime is equal to 1. Excuse me. So using distributive property again, this becomes B. Just rearranged. So A, B prime C, and then A prime, B prime C. So everything is already in max terms. B prime C is just equal to this. Combining all terms we have. So replace A by the equivalent, which is this 4 mean terms. So equal to AB C plus AB C prime plus AB prime C plus AB prime C prime, and then for B prime C, which is AB prime C plus A prime B prime C. Notice that AB prime C prime is common to both here, both A and B prime C. So we just write 1 because it's redundant. So we only have a total of 1, 2, 3, 4, 5 mean terms instead of 6, since A, B prime, C prime is common to both A and B prime C. So we have 5 mean terms. A, B prime C appears twice, and according to the theorem, 1 times x plus x prime is equal to x. It's possible to remove one of those occurrences. Rearranging the mean terms in ascending order, we finally obtain. So F, rearranging. We know that this equivalent of this is 0, 0, 1. So that's mean term 1. This is 1, 0, 1. The mean term 1, 0, 1. This is 5. There's an error here. This should be this is an error. This should be ABC primes or 0, 0, 1. One zero one. 101 is 5. These are the same. this is actually A prime B prime C, so it's lacking A prime here. A prime B prime C, that's 0 0 1, so that's M1. No, so not this one, but 1 0 0, so that's A B prime C prime. This should be A B prime C prime, so 1 0 0 for M4 and so on. So that's how you, therefore we found out that F, which is equal to A plus B prime C, is equal to this expression. Therefore F is just the sum of its mean terms, M1 plus M4 plus M5 plus F6, M6 plus M7. There are 5 mean terms. Mean terms 1, 4, 5, 6, 7. That this is the canonical form using mean terms for F. You can check the book, Morris Mano's book, for more example. Notation for sum of mean terms, for example 2.4. We can write this down, this function F, in sum of mean terms form. So the symbol used is, so the function f of a, b, c is equal to the sum of the mean terms 1, 4, 1, 4, 5, 6, 7. We already know the equivalent to this, m1. We know that m1 is 0, 0, 1, so 0, 0, 1, that would be a prime, b prime, and c. So it will be easy to convert between the two forms. An alternative procedure for deriving the mean terms of a Boolean function is to obtain the truth table of the function directly from the algebraic expression and then read the mean terms from the truth table. Yeah, you can use the truth table. In simplifying, reading the mean terms from the truth table. Yeah, so we can obtain first the truth table. We simply write down the inputs. We write down the inputs and then write the output for each of the combination of inputs. If we have the truth table, we know the values of the output. We know that the output is 1 for this combination of input. This is 0, 0, 1. And so as here. And we can easily say that this is mean term 0. Mean term 0, mean term 1, 2, 3, 4, 5, 6, 7. Therefore, f of ABC is equal to the sum of the mean terms 1, 4, 5, 6, 7. The same as this one. Sum of the mean terms 1, 4, 5, 6, 7. And again, we obtain the truth table value by substituting the set of inputs to the Boolean function or equation. Let's go to the next, product of max terms. To express a Boolean function as a product of max terms, it must first be brought into a form of OR terms. This may be done by using the distributive law. So we need to express it in OR terms. So using distributive law, we have x plus yz is equal to distribute the OR operation to over the multiplication. So x plus y times the quantity x plus z. Then any missing variable x in each OR term is ORed with xx prime. So instead of using x plus x prime, we are using xx prime, which is equal to the identity 0 for multiplication. Identity 0 for addition or operation. Since we are using or terms, so we need identity x prime. Example, the Boolean function, express the Boolean function f equals xy plus x prime z as a product of max terms. First, convert the function into or terms by using distributive law. So we use distributive law. We distribute xy, so xy or x prime, then xy or z. Then we distribute again here, the inside, distribute x prime to xy. So x or x prime multiplied by y or x prime. Then here x or z multiplied by y or z. Then what happened? We know that x or x prime is just equal to 1, so this term can be omitted. What remains is x prime y or y times x or z times y or z. This is now the product of max terms. Or is it? Not yet, because there are only 2 variables for each. We need 3 variables that are ORed. The function is 3 variables x, y, z. Each OR term is missing 1 variable, so therefore let's expand further. We add, for each term we add z prime. This is just equal to 0. Performing OR operation with 0 is the same, so we did not change this expression at all. We just added 0. Again, using distributive property, you distribute this to the rest. The expression becomes x prime or y, then or z, then x prime or y or z prime. Same with the rest. Then combining all terms, the result is, what is common here? X or z, x or y or z is common, so we can remove. We can only use 1, 2, 3, 4, 5, 6. What else is common? X prime or y or z is common too. So what is left is 1, 2, 3, 4. There are 4. 1, 2, 3, 4. Therefore, this is the final answer. F is equal to the product of max terms, and these max terms are 0, 0, 0. This is M0, remember? If it is not complemented, then it's 0 here. It's not complemented, it's 0, 0, 0, and that's max term 0. Here we have 0, 1, 0, 1, 0, which is 2. That's why it's max term 2. Here we have 1, 0, 0, which is 4. So max term 4. Here we have 1, 0, 1, which is 5. So max term 5. So F is equal to the product of the max terms M0, M2, M4, and M5. For the notation, f of x, y, z is equal to the product of max terms 0, 2, 4, and 5. See book for more examples. Next is, how are we going to convert between the canonical forms? We have two canonical forms, right? The product of, the sum of min terms, or the product of max terms. So how are we going to convert between these two? Let's check. So if we convert the function f, which is the sum, which has the min terms 1, 4, 5, 6, 7, we take, to be able to convert this into the product of max terms, we take the complement of f. We know that f prime, the complement of f, which is f prime, is equal to the summation of all the min terms that is not part of this min term. So which is not part here, we have 0, 2, 3. 0, 2, 3. So f prime is equal to the summation of the min terms 0, 2, 3. m0 plus m2 plus m3. Now if you take the complement of f prime by Demorgan's theorem, you obtain f in a different form. We take the complement of f prime. So f prime times the complement f prime of prime, we go back to f. Therefore f is just equal to the complement of m0 plus m2 plus m3. That is, by Demorgan's theorem, m0 prime dot m2 prime dot m3 prime, which is m0 times m2 times m3, which is now in product of max terms form. Therefore to convert f, which is the sum of the min terms, into the form product of max terms, we just take the subscript that is not in here, so 0, 2, 3, and that is the max terms of f. So f is equal to the product of the max terms 0 to 3, or f is the sum of the min terms 1, 4, 5, 6, 7. The last conversion follows from the definition of min terms and max terms as shown in table 2.3. From the table, it is clear that table 2.3, from the previous table. From the table, it is clear that the following relation holds. M sub j prime is equal to capital M sub j. That is, the max term with subscript j is a complement of the min term with the same subscript j, and vice versa. For example, f is equal to xy or x prime z. This is f is, if we convert this into the sum of min terms using the truth table. Using the truth table, we have this outputs, and the min terms are those with 1 values. So we can write f as equal to the sum of the min terms. This is min term 0, min term 1. So 0, 1, 2, 3. So 1, 3, 6, 7. So f of xyz is equal to the sum of the min terms 1, 3, 6, 7, or those with 0 value for f, for the max terms, or f is equal to the product of the max terms 0, 2, 4, 5. 0, 2, 3, 4, 5. Standard form. Terms that form the function may contain one, two, or any number of literals. For example, f1 is equal to y prime plus xy plus x prime yz prime. So this is a standard form as compared to canonical form, which is a complete representation of a function using min terms and max terms. Here, it doesn't necessarily have to be a min term or a max term. It can be any number of literals. That's for the standard form. Sum of products and product of sums of this function is shown in figure 2.3. Sum of products. If we say sum of products, so we are using OR operation on top of AND operation. So the final operation is using an OR gate. Then we have AND gates for the products. For the product of sums, the final operation is product or AND operation, so we use this AND gate. And then the sum, for the sum, use the OR gates, which is closer to the inputs. Comparison between two levels and three-level implementation. 3 and 2-level implementation. We know that AB plus C times D plus CE is just equal to AB plus CD plus CE. This is the distributed equivalent of this letter A. So, looking at which one would you prefer, this one or letter A or letter B? Which implementation is better? If we look at the both logic diagrams, this is more uniform and more balanced compared to this. And then they have the same number of gates, 1, 2, 3, 4, 1, 2, 3, 4, but this one is more balanced. And I think letter B is preferred compared to letter A because the delay is very important in logic circuits. Therefore, signals coming from the inputs must arrive at the same time to the output so that there will be no problem with the functionality and how we implement so that the output will get the correct or expected result. Both of the inputs must have the same delay going to the output. So I say that letter B is preferred compared to letter A. Because CDE or DE will have longer delay if we use letter A, if we use the logic diagram of letter A compared to letter B. AB will be faster, will arrive to the output faster compared to D and E. So I think letter B is better compared to letter A, provided that they have the same number of logic gates. Let's go to the other logic operations. We have NAND, NOR, exclusive OR, equivalence, inhibition implications. Let's see truth tables for the 16 functions of two binary variables. Then we have, that's for table 2.7, table 2.8, we have the Boolean expressions for the 16 functions of two variables. So table 2.8 and 2.7, this all go together. For f sub 0, the first function, this is null, binary constant 0, this is the constant. Whatever the input, this is constant, the output is always 0. For F1, that's AND operation. So X and Y, this column shows the operator symbol. The first column is for the Boolean function, the second column is for the symbol, and then the third column for the name of that Boolean function or operation. And the comments. So the 16 common Boolean functions, we have the constant, the null, constant 0, binary constant 0, which is null, then the AND operation, the inhibition. The Boolean function is xy prime. It's written operator symbol as x. Well, this is not commonly used. It's called inhibition. X but not y. Inhibition, x but not y. X, transfer. If your f of x equals 3, you are just transferring the value of x to f3. Inhibition again, x prime y but not x, you inhibit. It is x but not y, here x prime y, it is y but not x. Function 5 is equal to y, that's transfer, whatever is the value of y will be transferred to f5. f6 is equal to xy prime plus x prime y. Now this is the symbol for exclusive OR. Given the two inputs, x or y but not both. Either x or y is 1, but the other should be 0. That's exclusive OR. Then f7, x plus y. This is the OR operation. This is the NOR. We just negated or took the complement of the OR operation. That is x or y, then prime. The NOR operation symbol is a down arrow. So x nor y. Then equivalence. Equivalence is xy plus x prime y prime. So the equivalence is just the complement of the exclusive OR. X equals y. That's equivalence, is called equivalence. X equals y. Because the f9 is equal to 1 if both x and y are equal. Either both x and y are 1 or both x and y are 0. That will make f9 equal to 1 if x equals y. F sub 10 is equal to y prime, that's the complement, or not y. Then x or y prime, this is the symbol, means implication. If y, then x. If y, then x. Don't quite get that. You can explore it yourself if you want. Complement, x prime, we already know that, then x prime plus y. If x, then y. Another implication. explore it. Why is that? Let's go to F14. xy prime, that's NAND. You're negating the NAND operation or complementing the NAND operation. The NAND is symbolized with an up arrow. This is NOR and this is NAND. It's quite confusing because this is not usually used. But the symbol for exclusive OR is used more often. Then identity, f of 15 equals 1, binary constant 1. Now let's go to the digital logic gates. Bubble. This is the small circle in the output of the graph symbol of an inverter. We call it the bubble. Yeah, the symbol of the inverter. This is our inverter. And this one is called the bubble. To indicate, because the symbol of the buffer is just a triangle like this. This is the buffer. And whatever the input is just the output. Y is equal to X. In the actual circuit, the effect of the buffer is it has delay. In the actual circuit, it has delay. But for digital circuits, for analog circuits, we usually include a buffer intentionally so that we can add delay to the circuit. But for digital circuits, we want our logic gates to have minimum delay. So a buffer with a bubble becomes an inverter. That's the purpose of the bubble, to indicate that we are inverting the input. The small circle in the output of the graph symbol of an inverter. It designates a logic complement. The buffer, as I have already explained, this is triangle. It has a triangle symbol. The output is the same, the input used for power amplification of the signal, and is equivalent to inverters connected in cascade. Two inverters connected in cascade. Why did it say such? Because sometimes an inverter is easier to construct with transistors. So to make a buffer, you complement the inverter to make the input the same as the output. So in actual circuits, hardware, the buffer has more components, transistor components, than the inverter. That's why it said here that it is two inverters connected in cascade. And this is the complement of AND, NOR is complement of OR, as we have stated in the previous F14 and then F8, the NOR and the NAND functions. Let's go to the symbols, logic symbols, graphic symbol for each of the digital logic gates. Let's continue this. The next part of the video discussion for section 1.2. So let's end it here. Thank you for watching and please subscribe.